Hey, Chem 20s, I hope you're doing all right. We're jumping into the next section here, solubility, so what it means to dissolve and what we're actually talking about in terms of expressing dissolving in like numerical fashion. So we're looking at solubility. This first lesson is pretty note heavy. So I mean, if you want to try and go through this and read through and do kind of your own thing with this section, that's a-okay. If you want to follow along with the video, that's a-okay too. If you are doing your own thing, we are going up to page 21, but only the very, very top little bit of page 21 where it says communicating concentration ratios. So we'll do that in a later lesson. But if you want to do this on your own, try it out, and then you could always come back to the video later if you find it confusing. That's a-okay. But we'll roll through this as a group right now. So the idea with solubility, first thing that we talk about here, it's the maximum concentration of a solute for a particular temperature. The idea that it's for a particular temperature, and I'm sure you've seen this before, like you heat something up, you can always dissolve more, if it's a solid at least, dissolve more of it in there. So the amount of solute that can be dissolved is our idea of solubility. So it's putting that number on it. And I mean, one way to look at it, and this isn't the only way, we could say how much of the solute, that's the thing that's being dissolved, gets dissolved in 100 milliliters of water. Well, it doesn't necessarily need to be 100 milliliters. Well, there's lots of different ways that we can express solubility, but it's how much in a particular amount. So when we look at this, it's always solute, the ratio of solute, that's the stuff that's being dissolved, per unit solution. Per unit solution. So as we go through the various units that we see here for these examples, it could be moles per liter. That's moles for every 1 liter, so moles in a liter. It could be grams per milliliter. So how many grams in 1 milliliter of solution? It could be grams per 100 milliliter. So notice it's always this ratio of solute to solution, or 204 grams apparently for sucrose in water at 20 degrees, and it is again temperature dependent. So some definitions, and I'm sure you've heard these definitions before. Unsaturated means it has not yet reached saturation. Saturation, so we kind of got to go down here for our definition. It is the maximum concentration. So it's at a point where you can no longer add any more solute. No more solute is going to dissolve. So yeah, unsaturated means you're just below that limit. Again, note that this is temperature dependent. Temperature dependent. So that's sort of the idea there. Supersaturated means you've got more than you can dissolve at a given temperature, which is kind of weird, which is why we have this normally in there. So it contains more solute that you can actually hold or normally hold at a given temperature. So typically what happens is if you heat something up, we already talked about you can dissolve more solids if you heat something up, and this is what we're looking at right here. So you get a saturated solution at a higher temperature, and then you cool it down to a lower temperature where less of that solute should be able to fit, but it's still in there. And actually, you can check out some pretty cool YouTube videos of this, and it's like things coming out of a supersaturated solution. So yeah, pretty neat. So getting in, talking about some liquids. So some new terms, miscible and immiscible. Fancy terms, miscible means they mix. So they mix well, and you can dissolve and dissolve and dissolve and dissolve, and it's as if you have no maximum concentration, right? So you just keep on dissolving. Immiscible, when we're talking about liquids, they don't mix essentially, right? So mineral oil and water, they form a totally separate layer, so they do not mix at all. So miscible, mix well. Immiscible, doesn't mix at all. Don't mix. And then other things, I mean, we looked at this before. Elements have low solubility, right? So it doesn't matter if it's, you know, metals or non-metals. They typically all have very, very, very extremely low solubility. So just kind of keep that in mind. If you ever see an element in a question, it's always going to be low solubility, and expect very, very low concentrations. Cool. So So just a little reminder here, next big piece is a open systems, closed systems, and equilibrium and dynamic equilibrium. So some of these terms I'm sure you've heard before, others not so much. So open system, I know you've heard that in other science courses. This is matter and energy are free to come and go. So for example, a open beaker or an egg. An egg's kind of a weird example, but it's true. So energy and matter can come and go. Closed system is another one that we're looking at here. So in this case, no matter can actually leave, but energy is free to come and go. So a lot of systems that we have are closed. So you got a closed water bottle, right? That's a closed system. Energy in forms of heat can come and go, but the matter stays exactly the same. The planet Earth is actually considered a closed system, even though some matter comes and goes. It's compared to the size of the Earth, it's realistically nothing. The other one is not up here is isolated system. We're not really dealing with that very much here, but isolated system, that's no matter and no energy can come or go. Cool. So next couple terms are definitions to talk about are fairly new ones. So when you have equilibrium, it is for closed systems in which all measurable properties are constant. All measurable properties are constant. In other words, there are no visible changes. That doesn't mean that there's no microscopics, things that you can't see changes. It's just there's no visible changes. So for example, the color stays the same, or there's the same amount of solute at the bottom of a beaker with a concentrated solution of salt. Dynamic equilibrium. This is kind of an interesting one here, dynamic equilibrium. It's the balance between forward and reverse processes occurring at the exact same time. And we've actually talked about this before. We just haven't explicitly talked about it before. So big ideas with this. As a solution is produced, the solute must first dissolve and diffuse throughout the entire solution so that the concentration is uniform throughout. And actually, that's kind of a big thing. All of our solutions that we're looking at are going to assume that it is a uniform concentration throughout. You can just picture this for a split second, like you take some food coloring and you drip it into some water. It's not uniform yet. It needs to dissolve. It needs to spread all the way out before it's uniform. So we're assuming that it's already there. So as we reach saturation, no more solute will dissolve. That's where we get our equilibrium. So where nothing's really going to change. If we were to add any more solute, so add even a little bit more, it would just appear as little clumps. So here's our water. If I have more solute, it's just going to appear as a little clump down there at the bottom. And it's going to appear like nothing's really changing. Right? And that's sort of our next point here. It's going to appear that nothing's dissolving. But the particles are still in motion and there's still technically dissolving happening. It's just the stuff that is coming out of the solid and into solution is happening at the exact same rate as the solute that's in the solution. It's coming back out and it's going onto that solid and it's clumping onto it. So that rate coming out of solution is exactly the same as the rate coming into solution. This is actually a pretty big concept for Chem 30, the idea of equilibrium. So definitely know about equilibrium and dynamic equilibrium, how it's going forward and backwards. Now the place that we saw this, and here's sort of the big idea, the rate of dissolving is equal to the rate of crystallization. The place where we saw this is when we were talking about like, let's see, things that don't dissolve so well, and we were using the double-headed arrow. So this is showing that if I've got compound X as a solid and compound X as aqueous, it's actually going back and forth. So it's dissolving, right, as it goes this way. It's dissolving, but it's also crystallizing as it goes the other way at the exact same rate. So dynamic equilibrium. Cool. So that's a big definition we should know. So just a couple different, like this is just a nicer drawing of the things that we've drawn. So we've got dissolving happening here. We've got crystallization happening at the exact same rate. And if I'm at saturation, that's my dynamic equilibrium. You'll notice the double-headed arrow. It's going back and forth. So coming out of the crystal here and going back into the crystal there, again, at the exact same rate. So another kind of important Important little table to check out here. So based on a lot of experiments, generalizations can be made. Now, when we talk about generalizations, it means it's not true in every single situation, no matter what, but it's pretty darn close. So this is what we're learning here. So when I talk about solubility and temperature, for solids, we've already mentioned this a handful of times, solubility increases as the temperature increases. And that makes sense. I'm sure we've seen that before. Liquids, it's a little bit more difficult to find that generalization. It's typically not affected by temperature as much. There's other things that people look at for this, but gases, and gases is kind of a neat one for this. When we talk about solubility in gases, solubility actually decreases as the temperature increases, and that's something that's a little bit different and a little bit counterintuitive. The idea with this is gases like to be gases on their own, and they're more likely to be gases on their own if they're at a higher temperature. So even just think about boiling, right? You boil water or you heat water up to 100 degrees Celsius, it breaks those bonds, the water goes out into the atmosphere. Same sort of idea. It's more likely, it's got more energy, it's got more motion at higher temperatures, so it's more likely to escape from the solution at those higher temperatures. Cool. So yeah, I would definitely know solids and gases for this one. Solids are straightforward. We see that every day in our life. Gases a little bit different, right? Definitely a little bit different. So pressure. So you increase the pressure, so you're squeezing harder essentially. Solids not really affected. Liquids not really affected. But gases, oh, gases are affected. And you can think about this in terms of the gases. As you increase the pressure, it's like you're absolutely forcing those molecules down and into the solution. So no, pressure, yeah, not really nothing for, solids, liquids, but gases. Oh yeah, as you increase the pressure, you also increase the solubility. So something to kind of keep an eye on there. I think, let's see how doing for time here. Yeah, so I think we're doing okay for time here. I just wanted to check on that one. The next little section here is all about the concentrations, and we're starting to look more. So up to now, we've looked at qualitative analysis, and this is like identification of specific substances. It's about the qualities that we would see. So does it conduct electricity? Does it turn litmus paper a particular color? What substances are there, and how can we tell those substances are there? The next big section that we're looking at, and we're just going to have a little start on this today. We're not going to get too far, is quantitative analysis. So quantitative analysis is all about quantities or about numbers. So all about quantities and all about numbers and all about measurements is another big piece. So concentration is a quantitative analysis. It's all about those numbers. And when we talk about concentration, we mentioned this before, it is in fact a ratio between the amount of solute and the amount of solvent. And again, it doesn't need to be grams, and it doesn't really need to be in milliliters, but I think that's a good place to start to kind of think about this. So as we go through, I've got these two sort of little beakers here. I got beaker A and I got beaker B. They're both 100 milliliters of water, and therefore we're going to make 100 milliliters of solution. So the solvent, 100 milliliters of water. Beaker A has 25 grams of sodium chloride. That's quite a bit of sodium chloride. Beaker B has 5 grams of sodium chloride, significantly less. Same amount of solvent, different amounts of solute. A is definitely more concentrated, and it's very concentrated, and it's very easy to see. We could also say with this, so it's more concentrated, we could say that this is less concentrated for B, but we could also say that it is more dilute. Dilute. Perfect. So again, getting used to those different terms, and I'm sure you've heard those terms before. So really easy if the amount of solvent and therefore the volume of the solution is the same. Well, let's check this one out now. So example number 2, and the question for this is which beaker contains the saltier solution? So I'll put the video on pause if you want here. Try this out. Go ahead, put it on pause. If you said that beaker B has the saltier solution, yeah, you're good to go. So which beaker contains the saltier solution? In, oh shoot, in number 1, I messed this up a little bit here. So in example 1, let's have a look at that. In example 1A is saltier, and example 2, that's example 2 that we've got here, this is the one that you were just thinking about, which one is saltier? If you said D, you're absolutely correct. So we've got 20 grams, in this case, 20 grams of sodium chloride, right, in 100 milliliters. So we'll just pretend that the whole thing is 100 milliliters. For B, I've only got half as much volume, but I've got the same amount of solute, and you can see that it's definitely squished together a little bit, or is definitely more concentrated. So an easy way to think about this, it is 20 grams in 100 milliliters, 20 grams in 100 milliliters versus 20 grams in 50 milliliters is to make that bottom unit the same. So 20 grams in 50 milliliters, that's realistically 40 grams in 100 milliliters, right? And then what we're doing is we're doing the mass per unit volume, volume being 100 milliliters. So it makes it a lot easier if we put it into the same thing. So just checking out the next little piece here. Depending on the amount of solute and solvent, we prefer typically these terms that we've kind of already mentioned. So dilute is a small ratio of solute to solvent, whereas concentrated is a large ratio. So therefore, for number 1, I got to go back, example 1. Let's see. A was more concentrated, so let's just go down here. So the one that is more concentrated was A, the one that is more dilute is B. For the example 2, the one that was more concentrated was B, the one that was more dilute was A. So concentrated was B. I better double check that. Yes, concentrated is B. Nice. So your job for the next little bit here is to go ahead and check out the rest of this page. I believe it is page 20. Yep, page 20, and go through in each of the following situations, figure out what is the most concentrated, so situation 1, situation 2, and then situation 3, and really think this one through. Again, answer keys are on Google Classroom, and the big hint that I'll give you for this one is to make sure, if you can, put the amount of solution, so the amount of H2O, make that the same, and it becomes really, really easy. So don't do it in 200 versus 100. Make it all in 100, right? 100 milliliters of water. Anyways, nice short one. Practice up, and yeah, I think we're doing all right here. Remember, reach out if you ever need anything. Chem 20s. Have a good rest of your day, and we'll talk to you again soon. Bye for now.